In this game, two players take turns picking a number from either end of the array, and whatever they pick gets added to their own running score. Player 1 goes first, and both players play as smartly as possible to try to win. The narration should say that we need to figure out whether player 1 can end up with a score that's at least as high as player 2's. Beginner level, let's start simple. You have an array of numbers and two players take turns picking. Each turn, a player takes either the number at the very left end or the very right end, never from the middle. Whoever ends up with the bigger total score wins the game, and your job is to say whether player 1 can guarantee a win. Here's a surprise, we won't track two separate scores at all. Just one number will tell us the whole answer. Keep that in mind as we go. This exact setup, two players, both trying to play their best, picking from either end, shows up again and again under the name Stone Game on LeetCode. It's called a minimax pattern, which just means each player tries to get the best outcome for themselves while assuming the other player is also trying their hardest. Don't worry about the word for now. By the end of this video, you'll recognize this exact shape instantly. Let's print down the exact rules before writing any code. Player 1 always goes first. On every turn, a player takes either the number at index 0 the left end or the number at the last index the right end and adds it to their own running total. This continues until there's nothing left. One detail people easily miss. If both players end up with the exact same score, player 1 is still declared the winner. A tie counts as a player 1 win. Let's use one small example for the whole video. Nums 1, 5, 2 pies with player 1 moving first. The correct answer here is false. Even playing as cleverly as possible, player 1 still can't come out ahead. Hold on to this exact array. In a few slides we'll trace through it turn by hand so you can see exactly why. Before we dive into the solution, let's meet the Python tools we'll lean on. First, recursion, a function that calls itself on a smaller version of the same problem, the way a function summing a list could call itself on the rest of the list, until nothing's left. Here, our function will call itself on a smaller slice of the array, shrinking it from both ends. Second, a dictionary used as a memo, short for memory, something like storing the value 4 under the key 0 to save the answer for the pair starting at 0. Will we ever need it again? We just look it up instead of recalculating. This reuse trick is called memoization. Third, a two-dimensional list, a list of lists, like a grid starting out as all zeros in 2 rows, which works like a grid you read with dp at row I, column j. We'll build one version of the. Here's the idea most people try first. Every turn, just compare the two ends and grab whichever number is bigger. Watch it on 1, 5, 2 end. Player 1 compares 1 and 2 and greedily grabs the bigger one too. Now only 1, 5 remains, so player 2 grabs the bigger of those. 5 leaving player 1 stuck with 1. Final score, player 1 stuck with 1. Final score, player 1 has 2 plus 1, 3, player 2 has 5. Greedy loses. Grabbing the biggest number available right now isn't the same. Greedy loses. Grabbing the biggest number available right now isn't the same as player 1, 2. Here's the trick that makes this problem manageable. Instead of tracking player 1's total and player 2's total as two separate numbers, we track only their difference, my score minus the opponent's score. If that difference ends at 0 or above, player 1 wins. This turns a two-player two-score problem into a single running number. Let's call this the score gap. We'll use it for the rest of the video, so remember the name. This is the trickiest idea in the video, so let's go slow. Define diff of I, j as the best score gap achievable if we only played with the slice of the array from index I to index j. Say it's your turn on that slice. You can take the left number, nums at I, or the right number, nums at j. Suppose you take nums at I, now the opponent plays their best game on the smaller slice from I plus 1 to j, and their best result there is diff of I plus 1j. But that number is calculated from their side, so from your side it works against you and you subtract it. That gives nums at I minus diff of I plus 1j if you take the left. The same logic gives nums at j minus diff of I, j minus 1 if you take the right. Playing optimally, if you place out the recursive calls, you'll notice the same subslice. Like diff 1, 2 gets asked for more than once from different branches. Since it's the exact same slice of the array, it always gives the exact same answer, so recalculating it is pure waste. Left unchecked, this repeated work explodes as the array grows. This is exactly the problem our dictionary from earlier. The memo is built to solve. Instead of starting from the whole array and recursing down, we can build the answer from the smallest pieces up. We start with subarrays that hold just one number. Trivial. Since the entry for a subarray starting and ending at index 0 is simply the number at index 0, because a single number is stuck by itself. Then we grow to subarrays of length 2, then 3, and so on. And each new cell only needs 2 answers we've already filled in. By the time we reach the full array, the entry covering the whole range, from index 0 to the last index, this affix 0 is simply the number at index 0. This is the recurrence from before, typed out almost exactly. If I equals j, only one number is left, so we just return it. That's our base case. Otherwise, we first check the memo dictionary in case we've already solved this exact EIG pair. If so, we reuse the answer instantly. If not, we compute both options, taking the left end or the right end, save the bigger one in memo, and return it. This does the exact same calculation without the function calling itself. We fill a grid dp where the entry at I, j means the same thing as def of I and j did before. We start by filling the diagonal, that is subarrays of size 1, then sweep through increasing lengths, always building the entry at I, j from 2 answers already sitting in the table. No recursion means no risk of Python's call stack running out on a large array. Here's the whole function in one place. Nothing new. Just everything we've already walked through, assembled, so you can pause, read it top to bottom, or copy it and try it yourself. Let's plug in real numbers so this stops feeling abstract. Our array is 1, 5, 2. The pair starting at 0, 1 covers just 1 and 5. It's the bigger of 1 minus 5 or 5 minus 1, which comes out to 4, meaning whoever moves first on that pair ends up 4 points ahead. The pair starting at 1, 2 covers 5 and 2, the bigger of 5 minus 2 or 2 minus 5, which comes out to 3. Finally, the pair starting at 0, 2, our real answer for the whole array is the bigger of 1 minus the pair starting at 1, 2 or 2 minus the pair starting at 0, 1, which is the bigger of 1 minus 3 or 2 minus 4, which comes out to negative 2. A negative score gap. Now let's stress the table on a bigger example. After filling in every subarray length, dp at 0, 3 comes out to 2, 2, 2, 2, a positive score gap, so player 1 wins. That matches the real scores from the problem. Player 1 finishes with 234 points, player 2 with 12, and 234 minus 12 is indeed 2222. Quick pause before I give it away. What should predict winner return for numspo 22? No matter who takes which number, both players end up with the exact same score. So is the answer true or false? Pause the video and work out the score gap yourself before continuing. The score gap here comes out to exactly 0. And remember our rule from earlier, a 0 or positive gap still counts as a player 1 win, because ties favor player 1. 2 mistakes people actually make on this case, tracking player 1's and player 2's scores separately, which just adds bookkeeping for nothing, and writing the check as HT08 instead of HT0HT, which would wrongly return false here. You could write this exact same recursion and just skip the memo dictionary. It's shorter to type and still gives the correct answer. The catch, without caching, it recalculates the same subslices over and over, and that blows up fast. By the time the array has around 20 numbers, that's over 1 million repeated calls. Fine for a tiny example like ours, but too slow to rely on in general. Let's count the work. There are roughly n squared possible I, j pairs, one for every subarray, and each one takes only constant work once its 2 smaller answers are already known. So both time and extra memory land at O(n squared, meaning roughly proportional to n multiplied by itself. If memory matters, there's a trick. Since each length only needs the row below it, you can keep just one 1D array instead of the whole grid, cutting the space down to 1. Let's recap the whole journey. Grabbing the bigger number every turn feels right but fails. Remember 1, 5, 2 beating greedy. The fix was the score gap. Track the difference between the 2 players instead of 2 separate totals, then build it up from tiny subarrays to the whole array in O(n squared time. A single number is its own answer, and the same recurrence naturally handles every size above that. If you want more practice, look up Stone Game 2 and 3. Same core idea. With if you want more practice, look up Stone Game 2 and 3. Same core idea with a few extra twists. Then build it up from tiny subarrays to the whole array in O(n squared totals.